So next speaker is Professor Jim Jones. And the one thing I'd like to say about Jim is to congratulate him. He is an NSF Career Award winner, which is a very prestigious award for junior faculty, provides 5 years of funding, extremely competitive, and it's just a wonderful testament to the quality of Jim's work. So.
Thank you. I'm happy. Okay, so
unmute the microphone.
Okay.
This is the button on top.
I feel like I'm already kind of loud. All right. Okay, so today I'm going to talk about some of the work that we've been doing in terms of doing sort of dynamic analysis that allows us to track changes over time. And so built into the title is the idea of cause and effect and relating things that happen before with consequences of those actions. Nothing's more fun than a set of dominoes to show this effect. And here we have one that's colored red. And we could think of this as maybe a bug or any event of interest. So something that happens, we're particularly interested in that. We're interested in what needed to happen to cause that action and what that actually then causes. And we'll be talking about looking at this at both macroscopic levels and microscopic levels. And while dominoes are, like fun to look at just sitting there, what's even more fun is to watch them fall. So this is the idea of having actual motion and actually being interested in the complexities and all of the richness that happens when we take something that's just static and then make it dynamic. So macroscopic and microscopic, or as I put in the abstract, macrochronologic and microchronologic, which are both words it seems that I have made up because Google did not come up with anything for those. They often have similarities in nature. I found these two examples. So like a galaxy looks something like this, and an atom looks something like this, which are similar structures. And we'll see similar things when we look at the ways that we model software. So what do we mean? How does all this relate to software? Well, at a macroscopic level, you can't really read this very well, but this is a change log for a file. And here we can see a bunch of different versions, and different people with different log messages have committed those. And at a microscopic level, this is a view of the Eclipse debugger, which allows us to watch an execution or stop at a certain point to kind of see things that happen in the blink of an eye. So this is, we're talking about a span of perhaps years, and here we're talking about nanoseconds or something super fast. At the macroscopic scale, we have a number of tools that are already available to us. We see these like this is a Git log output, and built into sites like GitHub, we have kind of more visual forms of this kind of looking at time, like seeing how time has affected some software resources. And these are great, and I don't mean at all to disparage what we currently have. It's so much better than what we had just even a short time ago. It really does allow you to see a lot of interesting causes and effects and how things have changed over time. There are some limitations though. For example, with this view, we're looking at really coarse-grained artifacts. So we're looking at files, for example. And we're not actually seeing what it was. Like, we don't really have that ability to see what changed in these files. We also have fine-grained tools where we can actually see the changing code between two versions, which is also super nice. We can see code that was deleted, for example, here. We can see code that was added, and we can see change blocks. So these lines became these lines. Also great, but also has some limitations. In this world here, we're limited to 2 versions at a time. We often have these change blocks, and if you've ever had somebody go in and adjust the width of the code, or change the white space, and say make or remove, apply one of those automatic style things where it just moves the braces around or whatever, you'll end up having a whole file that changes into a whole file. And so we'd like to do a better job of actually disambiguating a lot of those changes. And this is a file at a time. So we're not looking at multiple files. So there's limitations on both sides. So what our solution to this was to build a model that represents all changes to the code. And this is just a simple version here, but we can see that in the first version, Sally committed it, and there's only 2 lines to this code. And then in version 1.1, she introduced a new line in the middle. And in version 1.2, then Ed then changed one of those lines, and so on. So we keep a multi-partite graph of every line of code. And we perform some analyses to disambiguate those change blocks. And by doing this, for every file in the entire repository, we can enable a number of really kind of more powerful and interesting ways to query and look at the motion of the code over time. So this is not that. This is a view of one of the visualizations that we've built on top of that data model that we've mined out of repositories. Here we can see code that has changed between a newer version and an older version, highlighted here in blue. But we can go even further. We can now say, now let's look at 3 versions, and we can see how that code has changed. We can zoom away and see even more versions. We can see how things have changed over time. And we can now incorporate another file to see what happens between these versions, between these files at each of these versions, which allows us to ask a number of more rich and interesting questions than we could have before. Dick, is that how many minutes I have left, or is that?
Yes.
Okay, thank you. That's including questions. Okay, thanks. In addition, you can see this bar here at the top, which zoomed up, we can see is a timeline. We can see month and year, for example. And we can see for each of these those 2 files that we were just looking at, that they were committed together at a certain point in time. And their change history kind of moved somewhat together into the early days, but then started to diverge. And this might be a hint of something interesting. Perhaps there's some code that was some dependency there originally, but maybe that dependency has been, loosened over time. There's a number of ways that we can utilize this kind of information. For example, if we have bugs in our software, we can automatically identify who should fix those bugs, or maybe who caused those bugs. And political issues aside, this could be useful, at least in terms of saying who has the right expertise to tackle a bug, given all the past authorship of the code. We can look at code clones. That's code that has been copy and pasted, and we can see when those things have been introduced, who did it, and if there are some patches that are applied to one, are they also being applied to others? And so we can do some automatic analysis to determine when we're going into bad situations. We can look at the sequence of changes that contributed to a security vulnerability. Just recently, there have been a whole slew of stories about all kinds of backdoors into SSL libraries and all kinds of things. There's the go-to fail bug that Apple has. And it might be interesting to look at what's the history there. Like, not just like who did that one commit, but let's look at this block of code and was it evolved that way over time slowly, and by whom? Was a network of developers or a single one? And so on. So we can answer a number of questions by having such models, fine-grained models of our software, and analyses that work on them. We performed a study where we had 24 participants. All were verified. We had some verification checks to make sure that they had enough expertise in programming in Java and so on, and knew how to use CVS and all of the tools that go with that. And we gave them a number of tasks. One of the tasks was identify the complete set of developers who ever contributed to a block of code. What's the original version for a code block? And coevolution, which is identify the versions that two code blocks were changed on the same day. So they could have been after each other, but within the same block of the day. And we varied the tools that they had. Either they were allowed to use CVS, Eclipse, the Eclipse plugin for CVS, diff. They could use the Control F to find. They could use basically anything they wanted to of the existing tool set, or they could use our. Well, in addition, they could use our visualization. And the results were just they were unquestionable. In terms of time to task completion, with the Chronos tool, they always got the result about half the time of the people who had the traditional tools, and their correctness was not even comparable. So when they finally turned in their answer, we had about 37.5% correctness on average for the authorship task. Went up to 100%. The original version task went 37.5 to up to 100%, and coevolution went from 0. None of them were able to get it done correctly, and up to 62%. So even our tool wasn't sufficient to make sure that everybody answered this perfectly, but we did a lot better. Okay, switching gears to the micro scale. Okay. So right now we have debugging tools that allow us to see execution. So these are a whole lot of instructions that are executing rapid fire, and we can put a breakpoint somewhere in there, and we can look at the state, and we can see what variables are holding what values at that point in time. Like I said, we have some similarities between the microscale and the macro scale. And at the micro scale, we are capturing the data flow at every instruction throughout execution. And you could think of this like a multipartite graph, where we have a set of variables, some state, and that can include stack and heap. And then when an instruction gets executed, the value here affected the values here, and we can continue this on. of course, this is not a very efficient, model to hold this information. So we're not actually keeping a true multi-part graph. But you could think of it that way. Theoretically, it is equivalent. So we can also look at instructions. So we could look at all the instructions and see what instructions are affecting what instructions, given those data flows that are occurring. So by doing this, and by watching executions, we can determine which instructions hold the most sway over other instructions. So what causes, cause what effects. And we have visualized these effects where we have a graph-based structure where these are individual instructions and their proximity to each other in the thickness of this edge is related to how often they affected each other. We have used this approach to identify somewhat emergent, I don't want to say architecture because it's not really architecture. It's emergent. It's this emergent structure of the code, like what if a code affects what code. So this is the gzip tool, and we can see that the core gzip code here, colored in like magenta, is highly related to util.c. But it shouldn't be that surprising to see util.c is actually split up. So the orange code here we see in a bunch of places. And that's because it's a general library that has different facilities that are used by different parts of the code. So we see lots of cohesion here. We have very little cohesion for util.c, for example. And so on, we have some other tools. This is sed. And we've gone a step further where we've actually introduced motion, much like the dominoes falling, where we can actually watch an execution running. So this is an XML reader, parser, processor, and writer. So you can see a lot of execution time is spent here, which is the reading and the parsing of the XML. And occasionally, you'll see a little flourish of activity that does some other actions, which is fun to see. And it might be helpful for diagnosing problems or activities or something like that. Much like we can kind of put somebody in an fMRI and see what brain patterns are happening for them. Or if a seizure is happening, where is that seizure located in one's brain? Okay, so this is, you might think, looking at those visualizations, this is all very fanciful and, trippy and whatever. So, I'll admit, these are probably not going to be the mechanisms that people will use. Maybe, I don't know, but I can see a number of potential futures that are enabled by such cause and effect analysis at the micro scale. For example, we can identify automatic breakpoints that are of interest. So if you say, I know for sure that this value is wrong or this output is wrong, we can suggest points in time and which instructions are most relevant to that output, both going forward and backward. So we can say, okay, what caused that and what is this causing? So have an infection here, what does that most affect? Whereas right now, you have to put a breakpoint at an instruction and you have to continue every single iteration through it. I mean, if anybody's ever used one of these tools, that can get very tedious. And we can identify all the set of cause and effects for such error infection. Okay, so I've kind of glossed over this. Both of these works are much more detailed, complicated, and it required a lot more actual work. The people who have worked on these things and done all the hard work are going to be presenting at the poster session at 12:20. So I encourage you to go there. And just to give you a little visual cue of who you should go and seek out, this is Francisco Servant, who does the macro scale code evolution, and Vijay, who does the microscale execution information. So with that, I will take any questions that you might have, if we have time. I think we don't.
How about one? One question. Sure.
Are you, speaking of the patentability thing, the motif, I suppose, are you is this patented or licensing out anywhere? Or
It's not.
Are you planning to?
I am, why do you ask?
Because I like it. I would buy it.
I haven't considered it. In the past, I have thought about doing such things. I mean, I'll be really interested to learn later about the issues that are going into this, but I feel like I don't have the muscle power to actually enforce a patent. I don't have the money to invest into such things, so.
The university.
Yes. Does the university have?
Oh, yeah.
Oh, yeah.
Oh, yeah.
Oh, maybe.
Maybe, all right, I'll maybe talk to you.
Thank you.
When you buy strawberries, you support the University of California, trust me. Strawberries. Strawberries. The University of California has more patents on strawberries than any other technology.